We're going to start chapter 16. We're looking at acids and bases. So we're going to have today and Monday to get through sections 1 through 4 of chapter 16, which should be plenty of time. And that's where the cutoff is for the exam. And then Wednesday, we're going to do a little bit of review for your midterm that's on Thursday next week. Okay. Sound good? Any questions before we get started on some new stuff? Yeah. Is it going to be the same size as the last one? Same length? Yeah, I think it's around 20 questions, so similar length. Yeah. Other things? Okay. So you probably have seen some acids and bases in previous courses. We talk a lot about pH, looking at if something has a pH less than 7, that makes it acidic. pH greater than 7, it's basic. You maybe have talked about, you've seen the definition of Arrhenius acid. We're going to go over all of those things, okay? So that's a lot of this introductory material for acids and bases. We will be doing more complicated equilibria, but that's going to be for the next midterm, just so you know, getting a heads up here. Okay, so some definitions of acids and bases. All right, so we are going to look at these, and they're going to increase in their inclusiveness, these definitions, and they're somewhat in their complexity. So the Arrhenius definition of an acid is it's a substance that produces H+. Okay, so a proton, you may see the term hydronium, okay, H+. Hydrogen ion. I'll use a lot of different terms. Okay. So given that, we can take what you may recognize as a strong acid, hydrochloric acid. We put that in solution in water. So it makes it aqueous, and we form H+ and Cl-. You will need, at some point this semester, coming up soon, need to remember which are the strong acids and which are the strong bases. So that's, you want to make a sticky note, put it somewhere where you'll see that frequently. That might be a good thing to start doing now. Okay, so there's a couple of ways that we can write this dissociation of HCl. This is the simplest way. The other way that we'll often write a dissociation or for an acid is including water as a reactant. And there are a number of reasons to do this, but for now, when we put HCl in solution, what we're going to find is that it produces H3O+, aqueous, and Cl-. So what is happening is that the hydrogen ion from HCl is forming a bond with the water molecule. And so we form what we call the hydronium ion. So with Arrhenius acid, we could say it produces H+ or it produces H3O+. Either one of those would work. Okay. Questions on that? Okay. At a base, the Arrhenius definition of a base is that it produces OH-. So if we put lithium hydroxide in solution, it's going to form lithium ion and hydroxide ion. OH- is hydroxide. So, as I keep saying, this Arrhenius definition is really limiting. Okay, and it's limiting in two ways. It only works in aqueous solution, which, to be honest, is what we're mostly going to be thinking about. But moving along in your life as chemists, however far you go, you're going to see other types of solutions, and you're going to need different definitions for acids and bases so that you can apply those in different situations, different solutions. And it only allows for one type of base, so it has to produce hydroxide. And there are other types of bases that exist. Okay? So we need a new definition. Sort of through time, historically, coming to more recent times, we have the Bronsted-Lowry definition, although still not that recent. So the Bronsted-Lowry acid donates a proton, and a Bronsted-Lowry base accepts a proton. Okay, so now we're thinking about the movement of protons, okay, through our reactions. This allows for non-aqueous solutions, so it's less limiting than Arrhenius. But it is not the most encompassing definition that we're going to talk about. We are going to also talk about the Lewis definition of acids and bases, but we're not going to talk about that until Monday. Okay, so let's look at an example of a Bronsted-Lowry acid. We said that a Bronsted-Lowry acid donates a proton. So if we go back to our HCl reaction with water, so here's our HCl, here's water, and what we see is that the H plus from HCl gets added to water to form H3O plus. And so the HCl is donating that proton to water to form H3O plus, and then also Cl minus is formed. Okay. Everyone see that? Okay. So we can take a look at these questions. What role does water play in this reaction? And by that, does water act as an acid or a base?
It acts as a base.
It acts as a proton. Exactly. It accepts a proton. It acts as a base because it accepts the proton. Okay. You probably maybe have come across the question of whether water is an acid or a base. What do we think? In this example, it's a base, but we will see other examples where it also acts as an acid. Yeah?
It's both an acid and a base?
Exactly. It's both an acid and a base. And it will do one or the other depending on what is in solution. So the other term that we're going to come across is conjugate base or conjugate acid. So in this reaction, chloride acts as the conjugate base. Conjugate base of HCl. It's what is left over after the acid donates the proton. We're going to see this in a little bit more detail, but I'm including these definitions now so we start to get used to them. And H3O plus is sort of what's left over after water acts as the base. That means that H3O plus is the conjugate acid. Conjugate of water. Okay. So what we're going to see are conjugate acid-base pairs. So in this reaction, water, H2O, and H3O plus, hydronium ion, are conjugate acid-base pairs. And then HCl and Cl minus are conjugate acid-base pairs. Okay, so here's a little bit more. Hang on 1 second. Excuse me. A little bit more about our structures of what we're calling proton and hydronium ion. You can use these interchangeably. If we're reacting an acid with water, you need to use the hydronium ion, not just H+. Okay. So if we take a proton, H+, and react it with water, we're going to get hydronium. Right? And in solution, if we have an acid in solution, the more correct structure that we would expect to find for the acid portion is the hydronium ion. It wouldn't just be H+ swimming around in solution. Okay. Okay, so this is one of my favorite acid reactions, acid equilibria. We're going to be doing a lot of equilibria with weak acids and with weak bases. But my favorite weak acid to write is HA. And the reason is that that can stand in for any weak acid that has one proton, right? And when you think about any weak acid as having a structure HA, where H is the proton and A is everything else, that makes every equilibrium problem look exactly the same, except for the numbers that you're going to put in there. And so I think it kind of simplifies things, at least it does for me. So this is our reaction of a weak acid. Okay. With water to form its conjugate base, A minus, and H3O plus, the hydronium ion. Okay, so HA and A minus are the conjugate acid-base pairs for that weak acid. And again, in this reaction, water is going to be acting as a base because it accepts a proton. So we're going to call it a weak base. And it's going to react and form the conjugate acid H3O plus. Okay, so these are our conjugate acid-base pairs. For every weak acid, doesn't matter if it's acetic acid, formic acid, the second proton of sulfuric acid. If you read HA, everything else other than the proton, that's the conjugate. Let's look at these two examples. One more thing before I point that out. You'll notice I have two different arrows here for these two reactions. I have HCl with a single arrow going towards the product side, and then I have HNO2 in equilibrium with its conjugate. Okay, so equilibrium arrows here in this second reaction. The reason being is that HCl is a strong acid, so it will completely dissociate in water, meaning there's no equilibrium with water. Okay, this reaction occurs to completion. Anything with a weak acid does not occur to completion. Okay, so we have this equilibrium in place. And that's why it's really good idea to start knowing those strong acids, because when we're calculating pHs of these two types of acids, strong versus weak, it's much easier to calculate the strong acid. So if you can recognize if it's a strong acid, you immediately know that the calculation is a bit easier. Okay, enough of that. Take a minute, work with your neighbor, find the acids, find the conjugate bases, find the weak bases and the conjugate acids, okay, for these two reactions. All right, how are these problems? Okay, cool. So for our HCl, this is our acid. And then the conjugate base, of course, is the Cl minus. Water then acts as a base. And H3O plus is the conjugate acid. Okay. Similar pattern here in the second equilibrium. HNO2 is an acid, NO2 minus, conjugate base. Those are paired. Again, water is acting as a base, and H3O plus is the conjugate acid. Okay, any questions on that? Hopefully pretty straightforward. We will get to a slightly more complicated situation when we have, here's a preview, when we have acids that have more than one proton. Okay, these can dissociate to form a substance that has one less proton. But now this can act as either an acid or a base. And then it can be kind of tricky to recognize which are the conjugate acid-base pairs in those. Okay. But that's a little bit later. So here I go, again, harping about knowing the strong acids and bases. Here's a nice list for you. Our strong acids include HClO4, H2SO4, which I'm going to put a star by, because only the first proton is strong. So what I mean by that is that H2SO4 has 2 protons on it. The first one completely dissociates in water. To get HSO4 minus. HSO4 minus is a weaker acid, so it has an equilibrium. Whoops, well, that's fine. With its conjugate base. Okay. But in your textbook, H2SO4 we listed as a strong acid. The other kind of nice thing is that all of our bases, they all have hydroxides, so they would all actually fall into the Arrhenius definition. At least for this list. Okay, so let's think a little bit about strengths of acids. So there's a nice figure in your textbook that has a list of a number of different acids, not an exhaustive list, but a good number of them. And the acid strength increases from bottom to top. So the highest, the acids at the top of the list are the strongest acids. And the first 3, I don't know how they distinguish which one was first, second, and third. They are all strong acids, and so they are probably pretty equal. Okay. The next block is a block of some of the weak acids. These are ones that we will likely be using. You'll see them in your homework, exams, and things like that. So you don't need to memorize them, but it's good to familiarize yourself with them. And then at the bottom of this list are species or substances that really aren't acids. They're included on the list because it is technically possible for them to lose a proton, but they have very negligible acidity, meaning they're very unlikely to actually lose that proton. So I put no proton transfer in water, and I think we can safely assume that. Our weak acids are those that are going to partially dissociate in water, and again, we're going to use those equilibrium arrows. They don't completely dissociate. When we put those in solution, we're going to have some unprotonated, some protonated. So protonated and unprotonated means It has the proton on it. So a good example is, we'll use HF because that's the shortest. HF, okay, and unprotonated, the H plus has reacted away, so F minus, okay. That's where what those terms are. And again, just like on the last slide, HCl, H2SO4, HNO3, those are our strong acids. There are a few others. They fully dissociate. We use a single arrow towards the products. So you should be able to look at this chart and recognize that HF is a stronger acid than H2PO4 minus, for instance. Okay. The other half of this chart include the bases. And the strongest bases now are at the bottom of the chart. And those that essentially don't act as bases are at the top. Okay. So the gap in the middle here are weak acids, and what you're going to see is that these are conjugate acid-base pairs across the chart. So we have H3PO4 and H2PO4 minus. That's our acid and conjugate base pair. Okay. All right. Any questions so far? Okay. All right. So that brings us to, I think this is actually section 16.3, although we have a little bit left in 16.1 or 2, I can't remember which one, where we are going to be thinking about the auto-ionization of water. Okay, so if we look at this term, ionization, meaning it forms ions, and the auto part meaning it does it automatically, okay? Automatically ionizes. Essentially what happens is that water reacts with itself to form ions. And those ions are going to be H3O plus, hydronium, and OH minus, hydroxide. So this is the equilibrium equation for for this reaction. Go ahead, take a minute and write out the equilibrium expression again. All right. How do we feel about that? So the equilibrium expression for this reaction is K equals H3O plus times OH minus. Okay. And that's it. The waters listed as reactants are in the liquid phase. So we don't include that in the equilibrium expression. So that is K. This is a special K. Water is special. So we give it the symbol KW. Okay, so using what you know from chapter 15, take a minute and calculate the hydronium ion concentration at 25 degrees Celsius. And Kw at this temperature is 1 times 10 to the minus 14. All right, so this is an ice table, okay? We don't know any concentrations of anything initially, right? And the concentration of water doesn't matter for our equilibrium. Water's a liquid, we assume that the concentration is constant. So what we know is that initially, we start out with 0 moles per liter of H3O plus and OH minus. And as the reaction proceeds, we form some amount X of those two species, looking at their stoichiometric coefficients here. So plus 1X for both. So then at equilibrium, we have X moles per liter of both H3O plus and OH minus. So plugging that into our Kw, we'll have 1 times 10 to the minus 14 equals H3O plus times OH minus, which is equal to X squared. Okay. If we take the square root of both sides, we'll get X is equal to 1 times 10 to the minus 7. And this is equal to both the H3O plus concentration, and even though I'm working ahead to the next slide, OH minus concentration as well. Yes?
Does this equilibrium equation mean that, like, when water is just in a cup on a counter, this reaction is currently happening?
Yes. Yes. So the question was, when you have water on a cup on a counter, is this reaction happening? Yes, this is what is happening. Cool. Other questions? Yeah.
So the concentrations of H3O plus and
The question is, are the concentrations of H3O plus and OH minus always equal? Yes, when there's only water in solution, they're always going to be equal. Other things? Yeah.
So are these ever given like a K value?
The question is, anytime you're given a K value, are you going to set up an ice table? Often, well, if you're going to be solving for equilibrium concentrations, yes, you need an ice Okay. So the next, but we know from this slide that OH minus and H3O plus have the same concentrations. They're both equal to X. Okay. The OH minus concentration here, maybe. All right. So now we go back to one of the topics that we talked about last time, which was how concentrations of reactants and products change with temperature. So we talked about the values of Kw changing with temperature, and that's true, or values of K, and that's true here with Kw. This equilibrium with water, hydronium, and hydroxide is endothermic. Okay? So if we have an endothermic reaction, does heat go on the reactant side or the product side? Reactant side. Okay. So if we increase the temperature, we're essentially putting more reactants into the equilibrium and forcing that reaction to go to products. Sort of stated here in the bold. Increasing the temperature shifts the equilibrium towards the products and K increases. Okay. So what all does that mean? So temperature is increasing. What about concentrations of products? Both H3O plus and OH minus concentrations increase, and they increase the same amount. We saw that at 25 degrees Celsius, our Kw was 1 times 10 to the minus 14, and the concentration of H3O plus was equal to the concentration of OH minus, and it was 1 times 10 to the minus 7. Okay. Calculate then at 50 degrees Celsius what the hydroxide and hydronium ion concentrations are. At 50 degrees Celsius, Kw is 5.5 times 10 to the minus 14. All right, what do we get for H3O plus, or H plus in this case, and OH minus? I got 2.35 times 10 to the minus 7 moles per liter. Anyone got that? Okay, so this is, again, taking the square root of the Kw. Same ice table setup as was at 25 degrees Celsius. Just different Kw value. So concentrations of H3O plus and OH minus are the same, right? Is the solution neutral? Yeah, so yes, the solution is neutral. This is the very definition of neutral. The concentration of H3O plus and OH minus are the same. That means it has to be neutral. But what if I tell you, if we calculate the pH of this solution, which we're going to get to next time, to calculate the pH, you take minus the log of the H3O plus concentration. So minus the log of 2.35 times 10 to the minus 7. We end up with a pH of 6.63. What's that?
It's a little bit acid.
Someone says it's a little bit acidic. Do you all agree? So, yes, you all, I'm not surprised you all agree. This is where I'm about to tell you that is a misconception. Right? Because at different temperatures, the pH's neutral line changes. Okay? So you were taught that pH equals 7, that's a neutral solution. Now what I'm saying is, at different temperatures, that could be higher or lower. Okay? If the temperature becomes higher, that neutral pH drops down. So yes, this solution is still neutral. Okay? By definition, H3O plus and OH minus are the same. The pH is 6.63. The definition of something that is acidic is that if the H3O plus concentration is greater than the OH minus concentration. Okay, so that is not true in this case, right? I love that problem because it's kind of what blows your mind a little bit. There's another really good one, pH, but I'll save that for next time. Yeah?
What about for bases? Will we have temperature like that in pH? Like, okay, what I mean is,
Yeah.
what if the temperature is lower? Say higher?
Oh yeah, so if the temperature were lower, Kw will become smaller than 1 times 10 to the minus 14. And then the concentration that we calculate will become less than 1 times 10 to the minus 7. So the pH becomes higher. So yeah, it would look like it if we assume the 7 would be
What about the reactional factors? They have the higher pH, like pH, and the other results. It will affect the reaction.
Oh, okay. This is a good question. So, if we're using water at a different temperature that's pH dependent, is that what you're saying? How does that affect the reaction? It could if that reaction is pH dependent. If it only occurs at a basic pH, you wouldn't want to heat up the reaction. Okay, that's what I assume. I don't do a lot of reactions in real life. But yeah, go ahead.
So if the concentration of those were even higher, the neutral pH would be different still.
Yes. Yeah. Yeah. So that neutral pH, it actually does fluctuate. But what we tell you is the neutral pH at 25 C. And for the most part, that's going to get you through most of it. You will likely see a problem like this. Okay. So when you need to know what the pH is, or to calculate the hydroxide concentration, or H3O plus concentration at a different temperature. We often, when we do like calculating pH, we're looking forward here, calculating pHs of weak acids at equilibrium, things like that. We are almost 100% of the time going to be at pH 7 is our neutral pH, so 25 degrees C. Other questions? Okay. All right, so then this table here on the last slide is calling those definitions of acidic, basic, and neutral, but only at 25 degrees C. Okay. All right, would we rather do more practice problems on conjugate acid-base pairs or leave early? Number 2. All right, this is what I have for the day. We will finish up our section 4 or whatever it is on Monday.